Good morning. Starting here in just a minute. Okay, so the first half of this chapter, we've really only been focusing on ionic compounds, which are metals and nonmetals. So what happens when we get into a situation where we have two nonmetals, which is where we have a molecular compound. That'll be where electrons are shared instead of transferred. If you notice on the periodic chart, when looking at our nonmetals, all their so predictable charges are all negative. So it'd be like two things coming together with two negative charges. And because they're not transferring electrons, there's no like net positive, net negative charge. So they don't stick together like an ionic thing does. So we won't be doing any charge neutrality with this. So don't flip-flop charges, none of that stuff when you're working with molecular. Hold on a second, my notes are giving me a hard time here. Really? All right, well, that's not working. I'll use that right now. That's okay. So we've got a couple different molecular compounds here. Methane molecule, this is carbon with 4 hydrogens. Ammonia, this is nitrogen with 3 hydrogens. And water, this is oxygen with 2 hydrogens. So the number of covalent bonds that the nonmetal atom forms is usually equal to the number of electrons it needs to achieve a stable electron configuration. So when looking at water, for instance, this central atom here is oxygen. And oxygen is in column 6. So that means it has a total of 6 valence electrons. So 1, 2, 3, 4, 5, 6. Everything wants to create an octet. So in order for this thing to have 8 electrons, it would need to have an addition of 2 electrons. Those 2 electrons end up coming from the hydrogen. That's why we have 2 H's that end up bonding there. Ammonium, this central atom is nitrogen. Nitrogen has 5 valence electrons, so it needs an additional 3. Here we've got carbon. Carbon has 4 valence electrons, so it needed an additional 4 to get it to that stable octet configuration. So what do we classify as a molecular compound or a covalent bond? So molecular compounds form when atoms of two or more nonmetals share electrons, and they form this thing called a covalent bond. Covalent bond, a very strong bond. Valence electrons are shared by nonmetal atoms to achieve some sort of stability. So valence electrons are the electrons in the outermost shell. We don't use any core electrons when bonding. And a molecule forms when two or more of the atoms are then hence shared. So let's talk about the diatomic molecules real quick. Hydrogen, we said, likes to form a diatomic, or it likes to bond to itself when it's in elemental form. So it forms this thing right here called H2. So we don't, like if you have a bunch of hydrogen in a container, we would never see it as just like hydrogens floating around like this. They'd always be paired off with a buddy. Why is this the case? Because it's more stable to have them bonded to a buddy than it is to have them by themselves. If we look at why that is the case, we can see here, hydrogen has one proton, so it also has one electron. So this would be its configuration. This hydrogen over here has got one electron, this hydrogen over here has one electron. They're far apart, there isn't any relative attraction. Well, when they get closer together, what they find is that if the two share these electrons or create sort of a unit, then they'll both have access to two electrons. And hydrogen, helium, lithium, beryllium, the first couple small elements, they're okay with two electrons. That's called a duet. They like to have just two. They won't have 8. We would never pack 8 electrons around a hydrogen. So look what happens when these two things get together is now they can share or pool together the totality of their electrons. Here they only had one. Now together as a unit, they have 2 electrons that they both can sort of use or access. And now they've got their duet. So this is why hydrogen forms that diatomic molecule. There's other molecules that do the same thing. Fluorine does the same thing, right? Remember, as far as the diatomics are concerned, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine are the things that form those diatomics. Fluorine has 7 valence electrons. Why does it have 7 valence electrons? It's in column 7. So this is close to having an octet, right? It just needs one more electron. So what happens is if these two fluorines move together and they share those 2 lone sort of sets there, what now happens is this fluorine has access to 8, and this fluorine has access also to 8. A lot of times when we have a shared set of electrons, we will put a line in there. So these ones out here, these are known as lone pair electrons, means that they're not involved in bonding. And then this central is the bonding pair. And again, the bonding pair, we will use a bar just to differentiate it from the other ones. So here are all of our diatomic molecules. These are all the things that naturally like to pair up in nature. Everything else will exist just as element or just as atoms stacked together in a row. But these guys are the special guys that like to pair to themselves because it creates a more stable configuration. So do know those. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So take hydrogen and then drop to nitrogen and just make an upside down L. So as far as sharing electrons between atoms of different elements, the number of electrons a non-metal atom shares is usually equivalent to the covalent bond that you'll find. Everything is trying to share in such a way that they get a noble gas arrangement or an octet. So over here, carbon and silicon, they are in column 4. So they have 4 valence electrons or 4 bonding electrons. So they will usually create 4 bonds. It's not always the case, but a lot of times it is. Nitrogen here and phosphorus, they have threes, or they have 5 valence electrons. So they need 3 to get them to the noble gas. So they usually form 3 bonds. Oxygen and sulfur, they can form 2 bonds. Sometimes you see them doing more than that. And then fluorine and chlorine, bromine, iodine, because they're in column 7, they only need 1 electron. They usually just form a single bond with something. So when looking at how these things come together, we draw these electron dot diagrams. And so we'll take, let's say we're doing methane. We've got carbon here, we've got hydrogen here. Carbon has 4 dots around it because it's in column 4, so it has 4 valence electrons. Hydrogen has 1 dot. Carbon would need 4 of these to fill all the empty spots, right? So we would bring it together, and then they'd have enough electrons to share. We would probably, instead of making these dots here, because all of these are bonding pairs, we would make those all as lines like this. And if this is starting to remind you for like 092 people of all the geometries, the trigonal planar and tetrahedral, you won't need to know those 3-dimensional shapes, but you will need to do these. So here are some common structures for a couple different things. So here's methane, looks like this. Here's ammonia, and then water. Are there exceptions to the octet rules? Always. The first one I kind of already told you about. Hydrogen likes to have just 2 electrons to form a noble gas arrangement. It likes to form a duet. Lithium will do that too sometimes. Non-metals such as phosphorus, sulfur, chlorine, and bromine can have what are called expanded octets. They can have 10 to 12 electrons instead of 8. The sulfur atom has an octet in a lot of compounds, but sometimes like this, we can end SF6, and here there would be 12 valence electrons, so it's an expanded octet. Sometimes we can form what's known as a double bond and a triple bond. A double bond is stronger than a single bond. A triple bond is stronger than a double bond. These here, everything you've seen thus far are all single bonds. It involves 2 electrons. Okay. A double bond is when we share 2 pairs of electrons, or a total of 4 electrons. A triple bond is when we share 3 pairs of electrons, or a total of 6 electrons. So when drawing an electron dot diagram, I don't really like their directions. I'm gonna sort of deviate from this. All right, so if you're given a formula like, what do I want to do? We'll do CO2 in a minute. I want to do something else. CCl4. Okay, so if I want you to draw the dot diagram for this, or the Lewis dot structure for this thing, the first thing I want you to do is count up how many valence electrons you get to mess around with. So how you do that is, well, carbon is in column 4. So carbon will bring 4 electrons to the table. They're all going to share all these electrons, so we're going to just sum them all up. So carbon brings 4. How many carbons are there? In this case, there's just 1 of them. Okay, so we multiply that by 1. And then we're going to add it to however many electrons chlorine brings. Chlorine is in column 7, so it's going to bring 7 electrons, and there are in fact 4 of them, so we need to multiply it by 4. So we add those all together, and we get a total of 32 electrons that we get to use. You can't have more electrons on the board than that. You can't, Ava, your cat is making me laugh. You can't have less electrons on the board. Is that, or is that a dog? I don't know. Dog? Dog, okay, yeah. So this is the magic number of electrons that you need to use, or the number of dots / lines. So once you've got this figured out, then we want to draw a basic structure for this thing. Usually whatever is written first is the central atom. You want to make something that looks balanced, okay? So I would put carbon in the center and then the chlorines would go on the side. I wouldn't ever do something like this. Chlorine in the center, and then one has a carbon, and then there's chlorines on the side like this, okay? This structure is not very balanced. In nature, things like to balance themselves out. So we would want to flip these two, right? We want carbon in the center. So we'll get rid of this. I don't like it. So once you have drawn your, what we call a skeletal structure, the next thing is to stick it together with single bonds. So if this is, this is the formula, right? So they have to be bonded. So I'm going to add bonds here. One here, one here, one here, and one here. So now it's all stuck together. Each of these lines represents 2 electrons. Remember that. So this line equals 2 electrons. So let's add up how many electrons we've used so far. 1, 2, 3, 4, 5, 6, 7, 8. Okay. How many electrons do we need to have on the board? 32. And everything wants to have access to 8 electrons. It all wants to get to 8. So I'm going to start filling electrons in. You always do the outer guys first and then work towards the inner thing. So always satisfy or add electrons to make the outer things happy and then fill your way into the center. So this chlorine over here, right now he only has access to 2 electrons. So I need to add 6 more electrons. All right, this chlorine over here, same thing. He only has access to 2. So I'm going to give him 6 more, same thing here. And this last guy as well. A lot of times it's sort of a repetitive thing because there's symmetry to it. So count up how many electrons we have on the board now. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Awesome, we have 32 electrons on the board. The last thing you want to do is make sure everybody has access to 8 electrons. Yes, there are exceptions. There are, 10 and 12, but for the sake of this class, really just make sure you're filling the octet. And then for hydrogen, make sure it's a duet. So, does everybody have 8? Well, I know the chlorines have 8 because I just filled electrons in to make them happy. So we just want to check the carbon and see, does he have access to 8 electrons? 2 from here, 4, 6, and 8. Everybody has access to 8 electrons. So this is a happy configuration. We would say that we are now done with that. Let's do another one. Let's do water, which is a really common structure that we see. H2O. Okay. Step 1, add up all the valence electrons that you have available. So hydrogen is in column 1, so it gives us 1 valence electron. And we have 2 of them. Okay, so we multiply it by 2. We add that to however many oxygens we have. Well, 1 oxygen, and oxygen is in column 6, so 6 valence electrons times 1 for a total of 8 electrons. I'm not sure what's going on with my writing board here. So our structure better have 8 electrons. Couple things, hydrogen always likes to be a terminal atom. That means it wants to be on the outside. It doesn't want to be a central atom. Why? Because hydrogen only wants 2 electrons. If we put it in the center, it's going to have way more than 2 electrons. So just always put hydrogen on the sides. So I'm going to put oxygen in the center. I'm going to put hydrogens on the sides. And then I need to start filling in electrons. So first stick it together, bond, bond. Then I need to get to 8 electrons. All right, so make the outer guys happy first and then work into the central atom. So we have 4 electrons on the board. Does this hydrogen need any more electrons? No, he doesn't. He's actually happy with a duet. Hydrogens also like duets or 2 electrons. Okay, so these 2 are both happy. So the remaining electrons need to go on the oxygen. So 2 here and 2 here. Does everybody have access to the number of electrons they want? Yes, the hydrogens have 2, and this oxygen has access to 2, 4, 6, 8. This is a 3-dimensional structure that you can rotate. So if your structure happened to look like this, that is fine. Those are the same thing. Okay, if you put your H's on top, whatever. But you do want to make sure that the dots are around the central atom. So let me hop back to the slides real quick. So we're going to look at CO2. Yeah. CO2. Okay, first thing we do is add up all the valence electrons we get to play around with. So carbon has access to, or carbon gives 4 electrons because it's in column 4. There's only one of them. Oxygen gives 6 electrons because it's in column 6, and there are 2 of them. So 12 plus 4, this is a total of 16 electrons. So if we're going to draw this, I'm going to put carbon in the center and oxygen's on the sides just to make it look balanced. And now I need to stick it together. So we're going to bond it together. And then I'm going to make the outer guys happy first, then work to the central one. So I have 16 electrons. I've used right now 4 of them. So this oxygen over here, I'm going to give 6 more electrons. 1, 2, 3, 4, 5, and 6 for a total of 8. This one over here, I'm going to do the same thing. 1, 2, 3, 4, 5, and 6. How many electrons are currently on the board? 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons on the board. What happens sometimes is students go, yay, I'm done. Well, now I need to check and make sure everybody has an octet or a duet. So the oxygens have octets. I know that because I gave them a specific amount of electrons to give an octet. When I look at carbon here though, carbon's looking a little sparse. What does carbon have access to? Right now, carbon only has access to 4 electrons. So a pitfall I see students do is they'll go like this. Oh, well, I'll just add 2 sets of electrons. Why can't you do that? Because you only can use 16 electrons. If we did this, we would have 20 electrons, too many electrons. Okay. So what needs to happen here is that the oxygens that have all these electrons, they need to share. So this oxygen is going to take one of these and it's going to bring it into a bond. All right, or we're going to make a double bond. You never want to do double bonds. You never want to draw double bonds until all the electrons are on the board. So make sure you get this check and then you can start playing around with double bonds if needed. Carbon has access now to 2, 4, 6. Could I take another one of these bonds and move it over here for a triple bond? I could, but that would make it sort of unbalanced. So instead, I'm going to have this oxygen use one of its sets and just move it over into this zone where it can then share. Okay. Whenever you're making double and triple bonds, I would always check and make sure that you have counted them correctly. So count up the number of electrons, 2, 4, 6, 8, 10, 12, 14, 16. I still have 16 electrons on the board. Is everybody happy? This oxygen has access to 2, 4, 6, 8. Oxygen is good. This oxygen also has access to 8, good. And now carbon has access to 2, 4, 6, and 8. Carbon is also happy. Okay. So everybody has 8 electrons. They've shared them in a great configuration to maximize that. Let's look at the diatomic nitrogen. So nitrogen likes to form this structure. Nitrogen, let's count up our valence electrons. Nitrogen brings 5 to the table, and there are 2 of those. So we get a total of 10 electrons to play around with. So I have 2 nitrogens, so I'm gonna stick it together. Nitrogen, nitrogen, I'm gonna put a bond. And then just pick one nitrogen to start filling in electrons. 1, 2, 3, 4, 5, 6, 7, 8. I need 10 electrons, so I'll put 9, 10 over here. All right, so we have 10 electrons currently on the board. This nitrogen is happy. He's got 8. This nitrogen, not so happy. So what needs to happen is this nitrogen needs to share some of these electrons. So I'm going to take, it doesn't matter where you take from. I'm going to take these here and I'm going to move them over to make a double bond. This nitrogen still has access to 8. This nitrogen has access to 6. So we're getting closer, but not quite there. So I'm going to take another pair from there and move it into this. So we have now a triple bond. There are still 10 electrons on the board, so we're still satisfying that. This has access to 8, and this one has access to 8, and we are good. We are done. If these 2 dots were over here or down here or something, that's okay. Again, it's a 3-dimensional structure. So I want you to draw the configure. I'm going to give you 2. Draw the configuration for NH3. And give me a second. Let me think about one that I want you to do. SiS2. Okay, so draw the Lewis dot structure for both of those. I'll give you 4 minutes, 2 minutes for each one. All right, so for these two, you want to add up valence electrons like we did with the other one. So this one should have a total of 8 electrons to play around with, 5 coming from the nitrogen and 3 coming from the hydrogen. So when drawing the structure, I'm going to put nitrogen in the center and the hydrogens on the sides. A couple of reasons I do that. One is it's more balanced than having like one of the hydrogens in the center. Another thing, hydrogen likes to be a terminal atom. It wants to be on the edges or the fringe. So we're going to stick this whole thing together. Take a look at if the outer guys are happy. So hydrogen only likes 2, so hydrogens are good. We don't need to add anything there, but I have to add 2 more electrons. The only place to put them is on the nitrogen in the center, and that makes an octet. So it's happy, we're good. Next one, 4 electrons coming from the silicon plus sulfur is giving us 6 times 2 for a total of 16 electrons. This is similar to the structure we did before. So I'll put silicon in the center and the sulfur on the sides. I'll stick it together. Then I'll make the outer guys happy first. So 1, 2, 3, 4, 5, 6, and then add 6 to this one. 1, 2, 3, 4, 5, 6. 16 electrons on the board. Silicon is not happy, so we've got to share some more electrons. So we'll take this off, create a double bond, and we'll take this one off and create a double bond. We still have 16 electrons on the board, and everybody has access to 8. So this is done. Okay. So, this says determine the arrangement of the atoms, calculate the valence electrons, add bonds when needed. So same thing that we went through. So when we're naming molecular compounds, if you've sort of noticed, you can have like a different number of oxygens, you can have a different number of sulfurs, it changes. So it's not as like strict or stringent as the metal and the non-metal where we flip-flop the charges. So because of that, when naming it, we are going to have to specify how many of each we have. So we'll name the first non-metal in the formula, and then we'll take the name of the second non-metal. We'll use the first syllable and we'll ide it. That is similar. But we're going to use a prefix in the front to tell us what the subscript is or how many of them we have. When vowels are O and O or A and O, we can drop the first vowel. So here are the prefixes: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. You do want to have those available or know them. So looking at this thing over here, this is 2 nonmetals. So I'm going to be using prefixes. I'm not balancing anything. I'm not flip-flopping anything. I'm just going to look at the subscripts and let that tell me how many of each I have. So carbon, I have 1 carbon. So it would be monocarbon because 1 is mono, right? But if you happen to have 1 on the first, you can ditch it. You don't need to keep it. So we're going to call this carbon, and then I have 2 sulfurs, disulfide. This here, again, carbon, we have just 1 carbon. And when you have 1 on the first, you can ditch the mono. So we're going to call it carbon, and then we have 2 oxygens, dioxide. I'm going to draw another one, though. If I write this thing, this would be carbon monoxide. We can't drop the mono if it's on the second thing. We only drop the mono on the first thing. And we don't drop 2, 3, 5, 7 if it's on the first, okay? We only drop it if there's 1 on the first. So looking at this, this should be, no, this should be nitrogen monoxide. Dinitrogen monoxide. I don't know why they're not adding the mono on any of these. This should be monoxide. Yeah, I don't like that. Sulfur dioxide, sulfur trioxide, sulfur hexafluoride. I'm not sure why they didn't put it in there. So when naming, name the first nonmetal by its elemental name the second nonmetal by using the first syllable of its elemental name followed by IDE, and then add prefixes. So looking at this thing right here, I've got NCl. I've got 1 nitrogen on the first, and I've got 3 chlorines. So we would call this nitrogen trichloride. One pitfall I have students do is they will like want to flip flop. So they'll say trinitrogen monochloride. No, don't flip flop with metals and nonmetals. All right, so I want you to name these here. SiCl4, P2O5, and Cl2O7. Okay, so silicon, in this case, we just have one of them. So we're going to just use silicon. And then we wouldn't say silicon chloride because we need to specify how many chlorines we have. So tetrachloride. We don't flip flop, so we wouldn't call it tetrasilicon chloride. The flip flopping only happens with metals and nonmetals. This one here, phosphorus, I have 2 of them. So diphosphorus, I have 5 oxygens, pentaoxide. And then over here, I've got 2 chlorines, so dichlorine, and then we have 7 oxygens, heptaoxide, or heptoxide. So number 1 here. So I think naming these is a lot easier than the metal nonmetals. You don't have to go through any process of flip-flopping. You just look at whatever this is and stick it, tack it on the front. All right, so write the name for each of these things using the correct prefixes. Okay, so when looking at each of these, the first thing you want to do always is identify what it is. So this is all of these are two nonmetals. If one happened to be, if the first thing happened to be a metal, we wouldn't be using this system. We wouldn't want to use prefixes. So this first one here, we've got two nonmetals, carbon, I've got one, so I'd call this carbon, and then oxygen on the second, and only one, carbon monoxide. Get to where the answers are. All right, I'll just write them out. So we've got carbon monoxide. This one here, I've got one nitrogen, so I can just go with nitrogen. Two oxygens, dioxide. This one here, one phosphorus, so phosphorus. Three fluorines, so that would be trifluoride. And then down here, I've got one carbon, so we go carbon tetrachloride. So writing formulas from the names, if we go in the other direction, write the symbol in the order of the elements that they're named in, and then just take the prefixes and make them the subscripts. So if you're given something like this, phosphorus pentachloride, that means I have phosphorus and chlorine in it. How many phosphorus do I have? Just one. Pentachloride means that as far as chlorine's concerned, I have 5 of them. Dinitrogen trioxide. All right, I've got nitrogen and oxygen. Nitrogen, I've got 2 of them from the di. Oxygen, I have 3 of them, O3. Sulfur hexafluoride, 1 sulfur hexafluoride would mean that I have 6 fluorines. If I write this here, Al2O3, we do not use prefixes here. What tends to happen is students will start to mix up all the different naming techniques, and they'll see this and they'll want to go, oh, dialuminum trioxide. Incorrect. We do not use prefixes anywhere near an ionic or a metal and a non-metal, okay? Prefixes stay just with molecular things. So this thing I would actually just call aluminum oxide. I don't need to put prefixes in there. It's unnecessary information because these have predictable charges that will flip-flop and tell me the formula from the name. Okay. So here's a good flow chart with everything in it that you may want to have accessible to, that kind of like guides you through what you need to do. So you start with identifying what is the compound. Is it ionic or is it molecular? If it's ionic, you want to determine, is it a metal or ammonium? With the non-metal, if it's the metal is one type of charge, or if it's more than one type of charge, you have to add a Roman numeral, and you just kind of go through this to get everything. So I would have that available when you're doing your test or your homework. All right, so just to check, let's go ahead. I want you to write the name of each of these things. This is sort of a mixed bag. There's a bunch of different things going on in here. All right, so this is a bunch of things that are all mixed together. So when naming them, you have to first identify what they are. So this first thing here is 2 nonmetals. It doesn't have a charge in the upper right-hand corner, so we're not talking about the sulfite polyatomic ion. So we're gonna name this like we would a molecular compound. So this is sulfur trioxide. The second thing we've got here is, so this is molecular. Okay, the second thing is ionic, specifically type 1, predictable charge. So I can just name the metal barium and the nonmetal chlorine, but I'll chloride it. Okay. This here is 2 polyatomic ions, so we'll treat it as ionic, but they're polyatomics. This is ammonium. And this thing is phosphite. We just have to reference a polyatomic ion sheet for those. This thing here, this is ionic, and this is type 2. So we do need a Roman numeral. So this is copper. I'm going to add a Roman parentheses. And then this is a polyatomic ion, carbonate. So let's cut this thing in half. The carbonate always forms a 2- charge. There's only one of them. So that means we need a 2+ over here, but there are 2 coppers to distribute over the 2+. So this should be copper 1 carbonate. This final thing here is molecular. We've got 2 nonmetals. So I use prefixes, dinitrogen, tetraoxide or tetroxide. 2 and 4, like if you're thinking, oh, that could get reduced down to 1 and 2, we don't reduce molecular, okay? Don't reduce molecular. So if you have something like this, we wouldn't reduce that down to 1 and 1. We would actually still call this thing disulfur dichloride. It's not going to let me write any further over there. Disulfur dichloride. All right, so don't reduce molecular. So I think the hardest thing is not the rules themselves and the processes themselves, but it's this step right here. When it's all jumbled together, what do I use when and where? So just make sure you're identifying each thing correctly. Electronegativity and bond polarity. So electronegativity is a value that indicates like how attracted an electron is, or like how greedy something is. So the higher the electronegativity, the closer the electrons will sit to it. It increases from left to right, going across, and it increases from bottom to top. So the upper right-hand corner where your helium is, that has the highest electronegativity. The lower left-hand corner of your periodic chart has the lowest electronegativity. So fluorine has the highest electronegativity, not including the noble gases. So fluorine is very, very greedy. The electrons will sit very close to fluorine. Frankie down in the lower left-hand corner doesn't really care a whole lot for electrons, so they don't really sit very close to him. So here is our highest electronegativity fluorine. This number of 4 is just sort of arbitrary. There's no units to it. Everything that falls off from there is in relationship to that 4 for fluorine. So we can see very low numbers over here, very high numbers over here. As far as bonds, nonpolar and polar bonds. So a nonpolar bond or a nonpolar covalent bond is a bond where they're sharing the electrons, but they're sharing them equally. Because they're sharing them equally, there's no polar quality or asymmetrical quality. So 2 hydrogens here, this would form a nonpolar bond. Now, if they're sharing electrons, so they're 2 nonmetals, but there is an asymmetry in the share. Like here, we've got hydrogen and chlorine. Chlorine has a much higher electronegativity than hydrogen. We would call this a polar bond because the share is kind of closer to the chlorine. So here are some examples of what we would say are non-polar covalent bonds. It's anything that has a difference in electronegativity of like less than 0.4. So nitrogen and nitrogen, 3 minus 3 gives us a difference in electronegativity of 0. Hydrogen and silicon, their electronegativity is so close. The difference between it is 0.3. We would still classify that as nonpolar. They pretty much share them equally. Now, a polar covalent bond is going to be two nonmetals that have an electronegativity that's 0.5 or greater, a difference in electronegativity that's 0.5 or greater. So like oxygen and chlorine, their difference in electronegativity is 0.5. We would say that's polar. Chlorine and carbon also has 0.5 polar. Oxygen and sulfur has a difference of 1. Where are these numbers coming from? It's coming from this chart here, okay? So the difference between these two numbers. So these share electrons, but they don't share them equally. Ionic bonds, which is a metal and a nonmetal, one way to determine that it's an ionic is that it just is a metal and a nonmetal. Another way is to look at the difference in electronegativity. If the difference in electronegativity is greater than 1.8, that means that the one thing is so greedy for the electron and the other thing is so indifferent to it that it'll just transfer the electron. So here they're not sharing the electrons asymmetrically, they're just giving the electrons away, specifically the metal is. So the difference in the electronegativity tells you what your bond will fall in. If it's less than 0.4, it's nonpolar covalent. If it's 0.5 to 1.8, it's polar covalent. And if it's greater than 1.8, it's no longer even in the sharing range. It is just ionic, where they're transferring electrons. So here's a kind of a visualization. Here the electrons are being equally shared. Here the electrons are being asymmetrically shared, kind of greedier over here. And here the electrons are just being transferred. So, let's see how we need to go over that. So we skip 6.7 in this chapter. So you don't do 6.7, which is like all the shapes. But we do want to talk about attractive forces within a compound. So here is a spiral of DNA. The reason that DNA curls in on itself in this double helix is because there are hydrogen bonds happening between adjacent groups. So a couple different types of, these are called intermolecular bonds or bonds that are happening between adjacent molecules. One of them is called a dipole-dipole attraction. And dipole-dipole attractions happen really just between adjacent molecules. It's when there's some sort of temporary dipole moment, and then they'll stick together. There are specific dipole attractions known as hydrogen bonds, and that was what we were seeing in the DNA structure. Hydrogen bond is when you have hydrogen adjacent to another fluorine, oxygen, or nitrogen. Those are especially sticky. So the molecules, the adjacent molecules will stick together. This I wouldn't classify as a hydrogen bond because it isn't hydrogen with fluorine, oxygen, or nitrogen. I would just call this a dipole bond. So these adjacent molecules will kind of stick together. That's why liquids hold together. But if this happened, instead of being a chlorine, it happened to be a fluorine and oxygen or nitrogen, we would call it a hydrogen bond. We have these things called dispersion forces or London dispersion forces. This is where you get a temporary dipole moment or a temporary asymmetry in the charge. So the nucleus, which normally sits in the center, will kind of swing to one side. The nucleus has a positive charge. The electrons get kind of clumped on the other side where there's a negative charge. And so now we have a positive and a negative side to the atom, and it'll sort of temporarily stick. But then that nucleus is always going to sort of settle back in the center. So that jostling that happens will temporarily fade out. These are weak but it does happen in nonpolar molecules as well to form liquids and solids. So these intermolecular forces, these hydrogen dipole bonds, hydrogen bonds, and dispersion forces are what allow things to be liquids and solids, especially if they're nonpolar. So they also have an effect on melting points. So the stronger your attractive force is, the higher your melting points are going to be. So if you only have dispersion forces, those temporary forces, your melting point will be really low. It's really easy to like turn you into a gas. If you have these stronger forces though, like hydrogen bonding, you are going to have a much higher melting point. And then the highest is going to be ionic. So if you have ionic bonds, where you have that three-dimensional lattice structure between metals and nonmetals, those have the highest of any of our melting points. And there's a diagram that sort of lays all of these out. So looking at some of the relative melting points, here's the dispersion force. This is the temporary, very, very low melting points. Like these are gases at room temperature. If we have a dipole-dipole attraction, that's where we have, you know, an unequal sharing of the electrons. It will stick to surrounding molecules. They have a little bit of a higher melting point. Hydrogen bonds will have higher melting points than just dipole-dipole because the hydrogen is combined with specifically nitrogen, oxygen, or fluorine is strong. And then ionic, look at how high ionic melting points are. They're like through the roof. So do know the relationship between those. Here is a visualization of some of those and their strength. So lowest strength is that temporary dispersion force. Then we have that dipole-dipole attraction. Then we have the hydrogen bond. Then we have just a covalent bond within, and then ionic at the top, which will be the strongest. Yeah, let's put us at time. So really quickly look through these and classify what you would expect as far as the attractive forces that are present. I'll give you just a minute to look at that. All right, so we can stay on point. So if we have this formula here, this is molecular. So it's going to be like dispersion, dipole-dipole, or hydrogen. I don't have any hydrogen with oxygen bonding. So I don't have hydrogen bonds. So we would call this a dipole-dipole force. This one here, H2O, this is molecular. And there is hydrogen combined with oxygen. So we would call that a hydrogen bond. So that hydrogen bond is actually going to be stronger than what we would see in A. This next one here, Br and Br. This is a nonpolar molecule. They're sharing the electrons and they're sharing them equally. So there's no asymmetry for the molecules to kind of stick together. So anything that's happening there would just be temporary dispersion forces. KCl, this is ionic. It's a metal and a nonmetal. And then NH3, this is hydrogen combined with nitrogen. Again, hydrogen combined with nitrogen, oxygen, or fluorine is going to give us hydrogen bonds. Those are going to be stronger than the dipole. So you will be able to want to pull those out. Okay, so that's the end of that chapter. We will call it for this week. Next week, we are getting back into math. So make sure you've got a calculator available and a notepad to be writing stuff down because you won't be able to do this stuff in your head. Otherwise, have a really good weekend. Enjoy the weather today because I think it's supposed to rain after that for like 6 days again. And I will see you next week. If you have any questions, personal questions, stay around.